Cool. Sorry, that cut out. Right. For the simulation, we have the array connected at a higher potential than the other side. So if I run the simulation, oh my God, I'll see that if I measure once the running man finishes stepping, come on. Okay, I'll see that the current going through this resistor and through the node is existent. So that means it was able to complete the loop and have current go from our voltage source over here to our load over here. Now, if I were to change it so that the load was on this side and the power source was from the battery on this side, and run the running man, I see that I have 0 amps. It literally will not allow the current to flow the other way. So yeah, that's like the whole idea of this intense circuit. The safety mechanism that will not break down, will not dissipate, will not be less efficient than a diode itself, and will make sure that we aren't destroying our entire solar system. Cool. If you have any questions about the sim or anything else ideal diode related, we can definitely talk about that later. It's a pretty cool circuit. Right, and our next, our main actually source of isolation, which is of course a safety mechanism, is our relay. The difference with this relay is that we've implemented a relay economizer, which is basically a current driver for the relay. What it does is it first activates the coil. So again, a relay has a coil and contacts. It activates the coil on the output. That means it drives enough current for the inductor or the inductor of the coil basically to close the contacts. But then to keep the contacts closed, you don't need to drive it at the current that it needed to start at or be first closed at. So what the economizer does is it makes sure it only drives the current at the minimal amount of of current to keep the contacts closed after the initial startup. And why this is useful is it really gives us savings in terms of power consumption. Because again, a coil is like a wound wire, and there's drop across it and power dissipation across it based on the current driven. And so, yeah, we want to minimize that as much as possible, and that's why it's called an economizer. And it's I think it's a pretty sophisticated IC. I mean, the inputs outputs that you really need, or you just need to enable it, and then it will start driving the relay. And with a few passives, it's able to regulate the current on its own. And there's also the fuse that is just rated for a bit more than the current that we expect to go through here. So it'll blow if it's surpassed somehow, something is shorted. And then the last thing I guess we can talk about, which I think is pretty interesting, especially for this board being how big it is and how much it has to do, is the layout. So it is a 2-layer PCB, and that proved to be somewhat difficult when designing it, especially with the digital interfaces, because routing like SPI and I2C to 6 different sections was difficult. And doing it all in the span of this like ground plane. So other key points of the layout before I just like walk through it a bit is that it has, as we've talked about before, the isolation between the grounds. It has connectors that are rated for high voltage and high current, and it's pretty linear in design when you kind of understand it. I mean, like, it might not make very much sense like if you haven't seen it before, but I'll try to explain it. And again, the digital trace routing was probably one of the more difficult parts of it in terms of layout. And the general direction, if I didn't explain it well before, of the power path again is from the MPPTs. The output goes through a fuse, and then it goes through a relay, last thing we want is the ideal diode, because if the ideal diode is like the save, like has to save everything, if there is a discharge into this board, ideal diode would want to be the first to like kick in and stop that and isolate it. And then it goes to the battery connector in the ideal current path. So looking at the board, each of these like duck sections, I don't know, better word for that, each of these like shapes, what it does essentially is this trace is the main power path. If you were to input your MPPT here to both the terminals of the barrier connector, it would go directly to the next MPPT through this kind of strip here. And then what's also necessary is for one of these terminals, the one that's at a lower reference in series, to become the ground reference. So that ground reference is then used for all of the for the ADC and the buffers and other components on the MPPT side of the isolation. And then it also has a SPI connector because the MPPT has a separate connector just to go to SPI. So then all of these sections have to be connected to the main ground digital controller board area through all of these isolators that sit across the isolation layer. So when we're here at the digital part of the ground plane, the signal communication, we see that, well, it's mostly on the bottom layer. So let me try to pull that up. Bottom. No. Yeah. So all of these like parallelly running traces have to like go from connect all the like clocks and all of the MOSI lines and all the data lines for all of these ICs. So that was kind of hard to route. And then they can't be concurrent with anything on the top layer for signal integrity purposes. So they have to, so how I routed this is everything on the bottom ran horizontally, everything on the top ran, what am I doing? Oh, what? Why is it like this? Oh, interesting. There we go. Everything on the top had to run more or less like vertically for this to kind of work out. And so it all interfaces with the controller board that sits here. And then we have, let me turn on, there we go. Turn on the overlay so you can see it. And then we have our thermistor connector that sits over here. So that's all where all the digital interfacing happens. But this interfacing is also kind of carried out through the relay because the contacts are part of the power path, but the coil is part of the same ground that extends from the digital communication, because we control the coil with ICs like the current driver that's referenced to this ground. So I had to continue the ground up here. It's kind of weird. But then we have our solenoid driver, the economizer. We have our ADC. Actually, this ADC is for the Hall effect sensor. We'll look at later. But that has to continue and has to be on this side of the relay where the coil is. And then we have the main power path, which kind of circles around the board. And that's because the main power path has to has to reference both terminals of the battery connector. And this is like the nicest way to do it from what I was playing around with the layout. So while we have the output of each MPPT connected in series, it then goes directly into, well, it first goes into the Hall effect sensor. That's not really part of the protection mechanism, but the sensor gives us an isolation to the ground reference again for the digital communication, which then goes as communication to the controller board. Also not easy to trace. And then it goes through a fuse. So here's a fuse holder. we populate our own fuse into that. And then out of the fuse, it goes into the relay. So you can see, like, I was trying to maintain as thick of trace as I could while keeping the isolation. And then the output of the relay goes to our ideal diode circuit, Q2 being a really big MOSFET, because again, it's the one that's constantly in the power path. This thermal pad is for that power dissipation. It's a really big FET, and it's controlled by our LTC 4359 that sits over here. So this is where all of the ideal diode circuitry had to sit. And again, like if you look at the layout, everything is really categorized by function, right? Like the layout is extremely important for this board because, of course, you have all the isolation, but also all the functions had to, one, be somewhat symmetrical, you know, the communication and everything, but it also has to sit in a position in the power path that would would make sense for minimal like distance traveled by like the traces. So the only like problem I guess I was finding when I was designing this is that to connect to the output of the, or sorry, to connect to the ground, I guess, when you're considering the power path, the return, which is the negative terminal of the battery, which is this trace, or the negative terminal of the voltage source, which is from the MPPTs. That ground kind of had to be referenced as like the reference for the ideal diode, because like logically speaking, when you have your ideal diode, you want to reference it to the output or to the lowest or to your 0 volts from your output of, let's just say, like 100 volts from all of these MPPTs. So what I had to do is run the trace from the first section in the MPPT all the way around and around, down and around to the ideal diode to use as reference. So you can see this blue trace on the bottom over here is for that. And so, I mean, it's not ideal, but it really shows you how the loop is like closed and how you have all of your protection mechanism here on the left. Just spacing wise, it was fitting pretty well and it keeps the linearity. And then the entire return path has to go around. But for this thickness of trace, it should be pretty fine. But we are still going to be testing this board, so we'll see. and then, of course, there are 2 of these boards in parallel again. And in the case of the, in the case of, zero work in this? No. Of the 5 MPPT board, okay, we're going to go back to here. Of the 5 MPPT board, this will be shorted so that we don't have the 2nd MPPT or the 6th MPPT being an input. So yeah, that's kind of the entire board. Does anyone have any questions about the board itself? Design-wise, any otherwise? Go ahead. Altium 365 is so cool. I'll never get over it. Okay, cool. And with that, that's really the end of this extremely long presentation. But solar is a huge topic and we're a solar car, so it kind of makes sense. Any other questions? Who do we still have? Cool. 3 presenters and 3 non-presenters. That's a good ratio. No questions. Cool. Well, thank you. Let me stop the recording.